Hi everyone, welcome to Chapter 6, which covers atmosphere and air pollution. In this chapter, we will be describing the composition and the structure of the atmosphere. We'll be explaining the importance of the ozone layer, the depletion of the ozone layer, and specific steps taken to address this problem. We will distinguish between indoor and outdoor air pollution and how these two types of pollution compare in industrialized countries versus less industrialized countries. We'll identify natural and anthropogenic, or in other words, man-made sources of air pollution. We'll explain the effects of air pollution on human health and the health of ecosystems. And finally, we will look at the Clean Air Act, which is a piece of legislation here in the US that governs air pollution, and talk about the impact that this has had on our air quality. So before we can get into all these matters of air pollution, we need to first talk about what air is and what the atmosphere is. So the atmosphere is a thin layer of gases that we call air, and it envelops the Earth. The atmosphere is a critical component of maintaining Earth systems and providing hospitable conditions for living things. It serves as a medium for transmitting heat and water vapor around the globe. It regulates the temperatures that we experience here on the surface of the Earth, and we'll talk more about how the atmosphere does this in just a minute. It serves as the source of gaseous carbon dioxide and oxygen that are used by living organisms in their metabolic processes, and it shields the surface of the Earth from external threats like harmful cosmic radiation. And we'll also look at how that works in just a moment. But before we do, a quick look at the composition of the atmosphere. So we've talked about how the atmosphere is mostly made of nitrogen before. 78% of the air particles floating around are molecular nitrogen. 21% are oxygen, and then every other component of air is pretty small compared to these two. Argon gas is the next largest, coming in at 0.9%, and then carbon dioxide at 0.042%, and all the other gaseous components bundled up together makes up the remaining 0.058%. When it comes to understanding how the atmosphere performs some of the important functions for Earth systems that we just mentioned, we have to look at the structure of the atmosphere because those functions are tied to its structure. So we think about the atmosphere as being divided into four different layers. The way that these layers are distinguished from each other is based on a number of different characteristics, including the temperature of the layer, the chemical composition, so in other words, what gases can be found in it, the way that those gases move or don't move throughout the layer, and the density of the layer. So there's a gradient where the layers that are closest to the Earth are more dense because the force of gravity pulls the air downward. The lowermost layer of the atmosphere is called the troposphere, and this layer extends from the surface of the Earth upward about 7 miles, or in other words, 12 kilometers. And within the troposphere, air flows and swirls continuously, and that activity allows both moisture and heat to be distributed across the planet. And it also plays a role in weather events because the troposphere is where weather happens. And the continuous movement of gases in the troposphere is tied to the temperature gradient that is seen within this layer. So as you move upward in the troposphere, the temperature decreases and gets colder. This is generally why it's colder at higher elevations, at the tops of mountains, that sort of thing. And in this illustration on the right, that's what the yellow line is showing. So you can see this zigzagging yellow line up the illustration. The yellow line represents temperature. So temperature is shown on the horizontal x-axis. So you can see as you move upward on the graph, the temperature drops. So the yellow line goes to the left, that's showing the temperature dropping. And at the Earth's surface, the average ambient air temperature is about 20 degrees Celsius, or about 68 degrees Fahrenheit. But at the top of the troposphere, so 7 miles up, it's negative 55 degrees Celsius, or 67 degrees Fahrenheit. Negative 67 degrees Fahrenheit, sorry. So why is this the case? Why is there this temperature gradient where it's warmer at the surface and cooler at the top of the troposphere? Well, solar energy, also known as solar radiation, this is what causes our planet to be warm. So remember from our previous chapters, the sun is the only source of new energy that's coming into Earth systems. So the solar radiation hits the Earth and causes the oceans and the land to warm. And then, like any object that has been warmed, the water and the land will give off some of that heat because the lower levels of the troposphere are closest to the Earth's surface, and this is where the largest amount of emitted heat gets concentrated. And therefore, the surface of the Earth is where you find the highest temperatures in the troposphere, with things getting cooler as you go higher because the Earth is giving off heat, so the lower levels get the most of that heat. Some of the solar energy that the Earth gives off gets released back into space, but a lot of it is retained within the atmosphere because of these gases that are referred to as greenhouse gases. This leads to what's called the greenhouse effect. So, the greenhouse effect is this phenomenon where the heat that's given off by the Earth gets trapped in the atmosphere by specific gases, which of course causes temperatures in the atmosphere to increase. And the short version of the explanation is that certain chemicals in the air block the heat that the Earth has absorbed from the sun and prevent that heat from escaping out into space. And this contributes to overall higher temperatures in the troposphere and on Earth's surface. And we'll talk more about the greenhouse effect in our next chapter on climate. But now that we understand why this temperature gradient exists in the troposphere, with the lower part being hotter and the upper part being colder, we can address how this contributes to the movement and the flow of air within the troposphere. So, in the troposphere, you get these things called convection cells, which are areas where warm air is ascending and cool air is descending in this circular pattern. And the reason for this phenomenon gets back to principles that we learned about in a previous chapter about how temperature works. So remember that temperature is a measurement of kinetic energy, and kinetic energy is the energy of movement. So remember, higher temperature means more molecular movement. So gas particles that are found lower in the troposphere pick up more heat energy that's being given off from the Earth, and therefore those gas particles are hotter and they move faster. And this extra kinetic energy means that they are spread out more and they become less dense, which causes them to rise upward because remember, less dense things float on more dense things. So the less dense air goes up. And then when the particles get to the top of the troposphere, it's cooler up there, and so they cool down too. And with less kinetic energy, their molecules move slower. And because they're not bouncing around so frantically, they occupy less space and they become more dense. And this causes the cooler air to sink. And the result is this continuous movement of air in this circular pattern called a convection cell. And this pattern contributes to what we casually know as wind. Wind is the movement of air from areas that are referred to as high pressure areas because it's more dense, so there's more air pressure, to low pressure areas where the air is less dense. And wind is part of our sporadic weather patterns, but there are also big trends in wind patterns and how wind occurs across the globe. One example of a particularly important wind pattern is referred to as Hadley cells, and that's what's being illustrated in this diagram here. So this blue blob is a sort of cutout of one small part of Earth. So the equator is being shown in the middle. You can see the little 0 degrees latitude labeled on the equator. And then on either side of the equator, the diagram goes up to about 30 degrees latitude north and then down to 30 degrees latitude south. So Hadley cells are the result of the fact that the Earth is heated more intensely at the equator, which causes the warm, moist air that has high humidity to ascend high in the troposphere at those equatorial regions around 0 degrees latitude. And the water vapor in that ascending air contributes to precipitation, which makes these regions around the equator very wet. But then at the top of the troposphere, the air cools and it's now very dry because it's lost all its water vapor through precipitation. And then it travels and descends back down at approximately 30 degrees north and south of the equator. And this influx of dry air at 30 degrees north and south of the equator contributes to a pattern that we see globally where deserts are more likely to occur at 30 degrees north or south. But we'll talk more about that when we get into biomes and deserts. For now, let's get back to the structure of the atmosphere. So we've seen the characteristics that define the troposphere. And at the top of the troposphere, there is this barrier that is referred to as the tropopause. And the tropopause is a boundary where temperatures stop decreasing as you go up. So that pattern that you saw, where the temperatures got lower as you go higher in elevation, it stops at the tropopause. And in fact, the opposite starts to happen as you continue onward into the next layer, as we'll see in just a minute. And the reason why this happens is because at this point, at the tropopause, you hit something called the ozone layer as you're getting up into the stratosphere. So the stratosphere is the layer that's just above the troposphere. It extends from the top of the troposphere at 7 miles above the Earth's surface all the way up to 31 to 33 miles. And the stratosphere's composition is distinguished from the troposphere in a few ways. One of these is that the stratosphere contains almost no water vapor. And another way is that it contains about 1,000 times more of a chemical called ozone, which we're going to talk about extensively in our next section of this chapter. But for our purposes here, all you need to know is that ozone is a chemical that absorbs much of the harmful UV radiation from the sun, specifically UVB and UVC radiation. We'll talk about that more in just a second. The sun actually produces 3 different types of UV radiation. There's UVA, UVB, and UVC. The ozone layer absorbs and captures all of the UVC and 90 to 95% of the UVB. So in that sense, it provides this protective shield, and it's also uniquely susceptible to warming because it absorbs this UV radiation so well. So because the ozone layer absorbs so much UV radiation, the temperature gradient that you see in the stratosphere is actually the opposite of what is seen in the troposphere. So in the troposphere, as you went up, things got colder. In the stratosphere, as you go up, things get hotter. So in our figure at the right, if we follow that yellow line, you can see that the temperature, it's zigzagging back in the opposite direction. The yellow line is going back to the right as you travel upward. And this is because the upper part of the stratosphere gets more exposure to solar radiation. It's closer to the sun, so obviously the upper part gets more exposure. And so it heats more readily compared to lower layers. As a result, the hot air is already at the top of the stratosphere. It starts off at the uppermost layer. And so, unlike the troposphere, you don't get this occurrence of convection cells of circulating air where the hot air is rising and the cold air is sinking because the hot air is already at the top. It has nowhere else to go. And so, this means that within the stratosphere, the air is relatively calm and doesn't experience very much mixing and swirling. And then moving upward from there, the upper boundary of the stratosphere is called the stratopause. And then past the stratopause, the next layer is called the mesosphere. And this layer extends from the top of the stratosphere, which remember is 31 to 33 miles, up off the surface of the Earth, up to about another 20 miles to 53 miles above the surface of the Earth. And one thing that distinguishes the mesosphere from the stratosphere is its lack of ozone. And so, therefore, because it lacks this chemical component that so readily absorbs the UV radiation from the sun, the temperature gradient again looks more like the troposphere. The temperature decreases as you go higher because the lower levels of the mesosphere they're up against the hottest part of the stratosphere. And so the lower levels of the mesosphere are catching all of the energy that's being emitted from the stratosphere. And then the top boundary of the mesosphere is called the mesopause. And then finally, the highest layer of the atmosphere is called the thermosphere. So this is considered to reach all the way up from 53 miles above the surface to 373 miles above the surface. So much bigger area than all the other layers. The thermosphere has an extremely low density of air, and its temperature gradient looks like the one that we saw in the stratosphere. Again, we can see that that yellow temperature line is zigzagging back to the right again. As you go up, the temperature increases. And this is because this layer is just so exposed to the sun that the highest particles capture the most heat. At the highest part of the thermosphere, the temperature of the individual air particles can reach 2,000 degrees Celsius, which is the equivalent of 3,600 degrees Fahrenheit. However, an interesting fact about the thermosphere is that because the density of the air particles is so low, it would still feel incredibly cold to your skin because the air particles there are so sparse that you wouldn't actually be able to perceive the heat that they are carrying.